Hey guys, welcome to the channel. The topic of this video is neuromuscular physiology. And you know what's so cool about this video? It's that this video is in collaboration with the PRECLINICAL Society at the University of Cape Town. In this video, we will be going through the different types of muscles and nerves, how nerves conduct an action potential, and last but not least, the neuromuscular junction. Now, let me hand over to Liama so she can walk you through the neuromuscular physiology.
Muscles in our body help us breathe, keep our body supplied with those good nutrients, hold us up, help us walk, lift stuff, work, read things, and just get jiggy with it, and all the other things we want to do. Without them, we would probably just be a pile of goo, just unable to do anything, which would not be fun at all. But we do have muscles, so whether you are reading, running from a bear, fighting like a Klingon, or simply pumping iron, bro, you are using muscles, both voluntary and involuntary. In this video, we shall explore how muscles work and what triggers muscles to work. Interesting fact, muscles comprise the largest tissue in the body, making up 40% of body tissue in healthy males and 32% in healthy females. Muscles can be categorized as striated muscles, which are skeletal and cardiac muscles, and non-striated muscles, which are smooth muscles. Muscles can also be categorized according to whether they are voluntary or involuntary. Voluntary muscles are skeletal muscles, and involuntary muscles are cardiac and smooth muscles. That's a lot of words. So let me define muscles as so. Cardiac muscles are involuntary and striated. Smooth muscles are involuntary and non-striated, and skeletal muscles are voluntary and striated. Today, we will focus on striated muscles, which are voluntary, otherwise known as skeletal muscles. Now, I do not know much about Romulan or Vulcan or even Klingon physiology, but I do know some things about human physiology, and human physiology is interesting. If you are a human, this is your physiology. At the neuromuscular junction, the neurons secrete acetylcholine, which when it lands on acetylcholine receptors on the muscles, triggers a series of reactions which cause the muscles to begin to contract, which causes you to be able to ask the question of, tell me what you want, what you really want, and therefore to perform all the other functions that you want to perform. But we are getting ahead of ourselves. First, we need to talk about neurons. There are many different types of neurons. Some are unipolar, others multipolar, and others pseudo-unipolar. Now, the question you have might be, Luckily for both of us, these neurons can also be classified as sensory, interneuron, or motor neurons. This classification of neurons tells you almost exactly what each neuron type does. Sensory neurons are responsible for detecting stimulus, otherwise known as sensing things. Interneurons are neurons which are responsible for being between other neurons, and therefore interneurons. Motor neurons are responsible for movement. Now, isn't that better? Now, because motor neurons are essential for all things movement and to do with movement, we shall discuss motor nerve physiology, and therefore how they are triggered to stimulate muscle contraction. When we look at the motor nerve, it has a cell body, an axon, and axon terminal. Motor nerve conduction is made possible by the differences in concentration of electrolytes between the neuron, and therefore the intracellular environment, and the environment outside the neuron, otherwise known as the extracellular environment. For example, at rest, there is a higher concentration of potassium inside the cell than there is outside the cell. But there is a higher concentration of sodium outside the cell than there is inside the cell. Therefore, both sodium and potassium have different chemical gradients. Overall, however, there seems to be a higher concentration of positive ions outside the cell than there are inside the cell, creating differences in potential and therefore an electric gradient. This electric gradient is maintained by the cell membrane. The difference in potential between the neuron at rest and the extracellular environment is typically 70 millivolts, but we write it as negative 70 millivolts. We write the negative to show that the intracellular environment is slightly negative in comparison to the extracellular environment. And we call this negative 70 millivolts the resting potential of the neuron. The cell membrane, which maintains this negative 70 millivolts, maintains a non-neutral environment. If something is non-neutral in chemistry, they say it is polarized. This polarization is essential for the conduction of neurons. When a stimulus arrives at the cell body of a neuron, it triggers the opening of gated channels. In the cell body of the neuron, gated sodium channels are usually opened, and the opening of gated sodium channels causes the movement of sodium down its electrochemical gradient into the cell, therefore depolarizing the cell. Depolarization means as the sodium enters the cell, it makes the areas around the sodium channel more positive and therefore moves the potential difference towards zero. In other words, it is making it more neutral. The stronger the stimulus, the larger the number of gated sodium channels that will open. And if more gated sodium channels open, the larger the area of depolarization. This is important because at the cell body, only a graded potential is generated, and a graded potential only spreads by current flow, meaning they only spread when the area adjacent to the depolarized area are depolarized as well. This means that the areas adjacent to the depolarized area are also depolarized due to the net presence of sodium. Graded potentials fade in strength with more distance away from their origin. We say they are decremental. However, an action potential can only be generated when the axon hillock is depolarized to between negative 55 and negative 50 millivolts. Therefore, we need a strong enough graded potential to cause depolarization at the axon hillock. This can be achieved by having a stimulus large enough to open more sodium channels, or a stimulus large enough to keep more sodium channels opened for longer. Failure to depolarize the axon hillock means an action potential won't be generated and therefore nothing will happen. However, if the threshold is reached, it is reached very slowly. But once the threshold is reached, an action potential is generated by the opening of voltage-gated sodium channels, causing a massive influx of sodium into the axon, causing rapid depolarization towards 30 millivolts, positive 30 millivolts of the area and the areas adjacent. This action potential spreads towards the axon terminal, at which point the calcium channels are opened. The entering of calcium into the axon terminal causes the secretion of acetylcholine from vesicles by exocytosis. Acetylcholine stimulates the muscles to contract and thus completing muscle contraction. But wait. We need to go back. Once the peak of 30 millivolts is achieved, the process of hyperpolarization begins in the areas previously undergoing depolarization. What this means is the sodium channels go from a state of open in which both the activation and inactivation gates are opened to being closed, and therefore a state in which the inactivation gates are being closed until the refractory period passes. Simultaneously, the voltage-gated potassium channels are opened, causing a massive efflux of potassium. This is called repolarization, and it returns the cell to a state of being polarized. During this time, when an action potential is generated and when the cell is undergoing repolarization, the axon is in a refractory period. The axon cannot generate another action potential. Once the resting potential is established, the efflux of potassium continues, however, until the cell is hyperpolarized. The sodium and potassium leak channels can then reinstate the cell to its original state, and therefore the process can begin again. Now, it is important that we know that there are different modes of conduction of an action potential, including saltatory conduction and non-saltatory conduction. Saltatory conduction occurs in myelinated neurons and ensures that conduction of the action potential is fast and efficient. Now that was a lot.
Wow, yes, Liama, that was a lot. Thank you for such a comprehensive tutorial. Alright, you guys might have noticed that the mind map looks much better than any of my other videos. And the reason for this is that I didn't make this mind map. This amazing mind map was made by Jessica. And as usual, you can find the link in the description box below. Or you can find it somewhere on Villa if you're a UCT first year medical student. Just don't forget to like and subscribe to this channel, because I am making a playlist for the Language of Medicine module in second year. And trust me, you will need it. Once again, a special thanks to Liama and Jessica for helping make this video. Alright, let's call it a day. Until next time, take care. This is the Caffeinated Medic signing off.